Hello dear students, welcome to the next part of the chapter Solutions. In the last part we have studied about ideal solutions and non-ideal solutions. We have studied about positive deviation, negative deviation. Very interesting thing to remember about positive and negative deviation. In case of positive deviation, all the things are greater or all the things are in plus. Whereas in case of negative deviations, all the things are less or all the things are in negative. But I would like to draw your attention to this point. In case of solutions showing positive deviation, their total vapor pressure is greater than that of expected ideal solution. Since the vapor pressure is greater, their boiling point will be less. Whereas in case of solutions showing negative deviations, their total vapor pressure is less than the expected ideal solution. Since the vapor pressure is less, their boiling point will be higher. Moving on to the next topic. Till now we have seen that Henry's law and Raoult's law are applicable for mixtures of volatile liquids. Since these are a mixture of volatile liquids, this can be separated by the process of distillation. But there are certain mixtures called as azeotropic mixtures which cannot be separated by simply distillation. They are called as azeotropic mixtures or constant boiling mixture. The Greek meaning of azeotrope is boiling without any change. So what are azeotropic mixture? The solutions or the liquid mixture which boil at constant temperature and can distill unchanged in composition. That means when we are carrying out fractional distillation of such liquid mixtures, even in the vapors their compositions remain unchanged and hence they are called as azeotropes. Now there are two types of azeotropes. One is maximum boiling point and another is minimum boiling azeotrope. Maximum boiling azeotrope and minimum boiling azeotrope. So let us study these one by one. I will begin with the first one, maximum boiling azeotrope. What are maximum boiling azeotropes? Just now we have seen that the solutions which shows positive deviations, their total pressure is greater than that of expected ideal solution, and since total vapor pressure is greater, their boiling point will be higher and hence they will be called as maximum boiling azeotrope. For example, the mixture of ethanol and water, the mixture which is obtained from the fermentation of sugar. This mixture boils at 78 degrees Celsius, whereas we know that the boiling point of water is 100 degrees Celsius and that of ethanol is 78.5 degrees Celsius. But the mixture of ethanol and water boils at 78 degrees Celsius. Sorry dear students, this is minimum boiling azeotrope, as the boiling point of the mixture is less than that of the components. Now when we carry out this distillation of this mixture, we do not get pure ethanol separately. Instead we get hardly 95% of ethanol, and that is what we call as rectified spirit. So what are the characteristics of minimum boiling azeotrope? Such mixture shows positive deviations. Their total pressure will be greater than the ideal solution and they will boil at a less temperature than that of the liquid components. So now let us study the next one, maximum boiling azeotrope. So the next is maximum boiling azeotrope. All those liquid mixtures which shows negative deviation, or I will say the solutions where the total pressure is less than that of expected ideal solution, they form a maximum boiling azeotrope mixture. Such mixtures will boil at a higher temperature than the boiling point of the components. For example, mixture of 60% nitric acid and 32% of water by mass is an example of maximum boiling azeotrope. There is one more example, 20% HCl and 80% H2O by mass. These two mixtures will boil more than that of their boiling points of their components. So dear students, why not to solve now some numericals based on Raoult's law and Henry's law. So here comes the first numerical. The vapor pressure of ethyl alcohol at 298 Kelvin is 40 mm of mercury. Its mole fraction in a solution with methyl alcohol is 0.80. What is the vapor pressure in solution if the mixture obeys Raoult's law? First of all, let us note down the things already given in the numerical. So, first of all, the pressure is given. Pressure is 40 millimeter of mercury, and this pressure is that of pure ethyl alcohol, and therefore we will take it as P0A. Now, the mole fraction is given 0.80. We know the formula. Now, PA equals to P0A XA. Substituting the values, we directly get the answer 32 millimeter of mercury. To start with, I have taken with a very simplest example. Let us move on to a little bit complicated example. This is your next numerical. Vapor pressure of chloroform and dichloroethane at 298 Kelvin at 200 millimeter mercury and 415 millimeter respectively. We have to calculate vapor pressure of the solution prepared by mixing 25.5 gram of chloroform and 40 gram of dichloroethane at 298 Kelvin, as well as you have to calculate its mole fraction of each component in vapor phase. Now, since we have to calculate the mole fraction in vapor phase, this becomes your one of the important numerical. To begin with, first of all, we need to calculate the number of moles for which the mass is already given to us. After calculating the number of moles, we can calculate the mole fraction and then we can calculate the vapor pressure. So let us begin. So these are the steps whatever I have told you. Let us first calculate the moles of dichloroform. The mass is given 25.5 upon the molar mass 119.5, and we get the answer 0.213 mole. Moles of dichloroethane, the mass is given 40 gram, the molar mass is 55, and we get the answer 0.470. The total number of moles by adding these two, we get 0.683. Let us calculate the mole fraction of chloroform, that is Na upon Na plus Nb. Number of moles of chloroform 0.213 upon total moles 0.683. We get 0.312. Mole fraction of dichloroethane can be calculated by the formula 1 minus Xa. So this becomes 1 minus 0.312 and we get 0.688. Now we have got the mole fractions and the vapor pressures of pure are already available with us. So hence now we can calculate the vapor pressures of solution. So let us calculate the vapor pressure of the solution. We know the formula Pa equals to P0A into Xa, or I will say vapor pressure of dichloroethane equals to pure dichloroethane pressure into its mole fraction. Let us substitute the value. This pressure is already given in the numerical 200. Mole fraction we have already calculated 0.312, and we get the answer 62.4 millimeter mercury. Whereas in this case the vapor pressure of dichloroethane pure is already given to you 4.15 into the mole fraction 0.688, and hence we get the answer 288.5. But we want to calculate the total pressure, so total pressure can be done by adding these two, and hence we get the answer 347.9 millimeter of mercury. So this is the answer of the first part we have got. Now the answer of the second part, we are supposed to calculate the mole fraction of each component in the vapor phase. So for calculating the mole fraction in the vapor phase, we use the formula. The mole fraction in vapor phase equals to pressure of CHCl3 upon total pressure. This we have already seen, and I have told you that this is one of the important formulas in my last video. Let us substitute the values. Pressure of CHCl3 we have already calculated 62.4 upon total 347.9, and thus we get 0.18. This will be the answer for chloroform. Now let us substitute these values. The vapor pressure of dichloroethane we have already calculated 288.5 upon total pressure is 347.9, that is equal to 0.82. Dear students, here it's not 4.15, it is 415. So got the answer, got the solution. This is your next numerical. Two liquids X and Y on mixing forms an ideal solution. The vapor pressure of solution containing 3 mole of X and 1 mole of Y is 550 millimeter of mercury. But when 4 mole of X and 1 mole of Y are mixed, vapor pressure of solution becomes 560 millimeter of mercury. What will be the vapor pressure of pure X and pure Y at this temperature? Now in this numerical there are two cases. In first case there is mixture of 3 mole of X and 1 mole of Y. Whereas in second case it is 4 mole of X and 1 mole of Y. So I will say this will be total number of moles will be 4, and here total number of moles will be 5. So using this now we will solve the equation. So using the formula, total pressure equals to P naught A XA plus P naught B XB. Now A and B I have replaced by X and Y so that I can correlate it with the numerical. There are the two cases. P naught X or P naught Y, these values are not mentioned in the numerical. We are supposed to find out it. So I don't know its value. But the mole fraction of X, in the first case total moles of X is given 3 and total moles will be 4. Similarly, the vapor pressure of pure component Y is not given, but the mole fraction of Y can be calculated. 1 mole of Y and total number of moles will be 4. In second case, again we don't have the value of pure component X. Mole fraction can be calculated. 4 moles of X upon total mole will be 4 plus 1, 5. Again we don't have the value of pure vapor pressure of Y. Mole fraction of Y, 1 mole of Y upon total mole 5. Now these are the two linear equations of two variables. I hope all of you know the calculation of these two. So by solving these two, we get the value P naught X equals to 600 millimeter of mercury and P naught Y equals to 400 millimeter of mercury. So the numerical sounds to be very typical, but it's very easy, hardly two-step answer. The hint is that you must be able to calculate the mole fraction from these given things. Okay, dear students? So this is the assignment for today's video. These two numericals you will try now on your own and write your answers in the comment section. Thanks for watching. Have a nice day.